Calculus AB, Chapter 1, Section 2. Today we're going to look at just day 1 and work on notes and discovering limits. So the limits that we're going to be concerned with today are the numerical approach and also using a graphical approach, looking at, the pictures, the functions. What is a function? Well, here is the mathematical way of writing a limit. The limit as x approaches c of some function, f of x, in here I could have this as x squared plus 4 maybe as my function. But there's some function, and as I approach c, my limit is some number L. You can see there's the quotes, that's how that's read. We also, rather than coming into some constant value c, maybe it's 7, maybe it's -3, we can also look at what happens to the function as x approaches infinity. Or we could even look at what happens if I approach -infinity. That also could approach some value L, some number value. With limits, the notation means that the values of f of x of the function approach or are equal to L as the values of x approach but do not equal c. So I just need to be coming into c from the left and the right. I don't have to be right at c. Graphical approach of a limit. I'm going to clear the screen and we'll start again. So, example number 1. Let's see, what do they want us to do? Right up here. The limit as x approaches 1. Well, as I approach 1, from the left side, I would be up in here somewhere as I get close, right? From the right side, I would be up in here somewhere as I get close to x equals 1. Well, these two are driving together, aren't they? They're headed towards each other. It looks like it's a height of 2. The limit would be 2. The value from the left must agree with the value from the right in order for a limit to exist. Here was the function that we were concerned with, x squared minus 1 over x minus 1. Second one, limit of g of x as x approaches 1. So once again, we're coming into 1 from the left side and then the x value from the right side. Well, if I travel upwards, as I get close to 1, I'm on the function right there. As I come in from the right side and travel up till I intersect the graph, I'm right there. These two are coming into a y value right at there. This also has a limit of 2. You may say, well, what about this? At 1, I get out 1. Why is that not the limit? Well, limits are concerned what's happening around this value as x approaches 1. Not what happens at 1, what happens around 1. And what happens around x being 1 is it gets a height of 2. Third one, see if you can figure it out. As x approaches 1, well, this whole thing really is just one solid line. They make a particular emphasis at 1 there. The value would be 2, but it's just another point on the line. Well, then as we approach 1 from the left or the right, we're driving in again at a height of 2. Left side, right side must agree. Why would we ever want to study limits? Well, limits can be used to describe continuity. Is a function continuous? We can talk about that with limits. And also, limits are used to help us define the derivative and the integral, which are really key ideas in calculus. Matter of fact, we kind of think of them as the foundation of calculus. So limits are very important. That's why we start studying them from the very beginning. Make sure everybody understands this. Graphical approach to limits. So we've got this complicated function. I want you to try and fill in this chart. This should be a very easy question. What is it saying to you? To me, I'm looking at, well, there's some function f. Okay, that is the graph that I'm looking at. This is an x value at 0, isn't it? What is the function's value at 0? When I put in 0, it appears that I get out an output right there, which would be what, a height of -1. So the y value is -1. The limit as x approaches 0 from the right side, so as I come into 0 from the right, travel till I hit and intersect with my function, it too has a -1 value. From the left side, as I come into 0 from the left side, travel till I intercept my graph, it too has a value of -1. Therefore, that's what 3 dots that are kind of triangular in shape there mean. Therefore, my conclusion about the limit at 0, based on the right side and the left side, is the function has a limit of -1. The left side equaled the right side, and therefore the limit exists. Let's look at the middle one. -3. What is the function's value at -3? Well, at -3, the function's value would be a height of 1. -3 from the right side. So as I follow my graph and I'm coming in from the right side, and I'm hitting into this zone of -3, I just got an idea here. Let's kind of put in -3. So we're right in this area. I'm approaching that. Well, that kind of appears like it's kind of similar. I'm going to call it 1. From the left side, okay, so I'm coming in from the left side. That means I'm traveling down this function, aren't I, as I come in? Well, these two are agreeing there, aren't they? It appears to be 1. You know, it looks like it might be just a little bit bigger than 1. I'm just going to stick with 1 there. Therefore, the limit as x approaches -3, I've considered the left, I've considered the right, backwards, but left and right, they agree it's 1. So they're equal. Moving on to my third one. You could almost make an argument that this was 1.5, couldn't you? I'm going to update. Let's go 1.5. But I screwed up. Leave that one at 1 because that dot is definitely at 1. Okay, third one. F of 1. When I put in 1, I get out -1. When I approach 1 from the right, what do you see? Well, if I'm coming into 1 from the right-hand side, I'm traveling on this function here, which takes me up to a height of about 2, doesn't it? If I travel into -1 from the left side, now I'm hopping on, I guess I'm on this segment because I'm coming into 1 from the left side. That places me down here in this region. Well, that value is -1. So therefore, the limit as x approaches 1 of f of x is dne. Why is that the case? Well, the left side does not agree with the right side. Notice we got 2, we got -1. They do not agree. So, graphical approach to limits. Problem 21. Take a moment, write out your answers, and then, so just pause this and come back to it. I will fill in my answers. So there are my answers. Check to see how you did 21 and 22. And if you have any questions, put a mark by them and we'll talk about them in class. Hopefully we have similar answers. Graphical approach. We got a little bit of time. I was just watching my time here. So, graphical approach as numeric values approach limits. The discussion above gives an example of how we can estimate a limit numerically by constructing a table. And we can also graphically draw it on the graphing calculator. Estimate the following limit numerically by completing the table. And we want to look at this function right here, correct? So as it approaches 2, I'm really interested in what happens at 2. So let's let x get close to 2 from each side. So over here I started at 2 1/4, but I'm working my way in to 2.001. On the left side, we're at 1.75, and I'm working my way into 2, coming up to 1.99. So please take out your calculator and put the function in, and then we can use the trace function on the calculator to help us find these values rather quickly. And then we can compare it as x approaches 2. I'm going to pause for a moment. You can do likewise. Okay, so what I've done is I've gone to y sub 1, I've put in my function, I'm going to hit graph, you do likewise, and there it is, it's a linear function, and we could expect that because look at how this would factor x plus 2 and an x, what is it? Oh, it's actually x minus 2. It doesn't factor nicely? Okay, we'll leave that alone. All right, well, I'm going to go on. Let's hit trace, and what I want you to do, if you hit trace, I've got some funky stuff going on here. So if I hit trace, and I want to trace at the point x equals 1.75, it will reply with my y value of 0.75. Next, move on, I'm going to hit trace. I want to know at 1.9. Just a quick way of getting it to analyze the points, and this would be 0.9, and so on. So go ahead and fill in your... Okay, so I got my chart filled out. Oops, I see I missed the last one because my calculator was sitting on top of it. But there's my results from doing the trace function on that when I was on the graph screen of my graphing calculator. What the question is what is the limit as x approaches 2? Well, from this table of values, and AP loves to do tables, they think you should be able to, gain information from tables and be able to read it. What is happening? Well, the thing I noticed when I put 2 into my function or my calculator, I got nothing back out. Basically, it's undefined at 2. If I put 2 in the denominator, notice how this goes to 0. We cannot divide by 0. So 2 is an undefined value for this function. And I don't know what my problem was before, but this really does factor, doesn't it? It's an x minus 2 and an x minus 1 over an x minus 2. And we can see, I think you remember this from pre-calc, those two would actually cancel away. It gives us a whole discontinuity at 2. So this thing really acts a lot like a linear function. And it kind of falls into x minus 1. So if I put in 1.75 minus 1 gives me the 0.75 value. And you can see how those are easy to come out with. So what is the limit of this? Well, as I approach 2 from the left side, it's getting into 0.9999, it looks like. And from the right side, it's 1.001. I think this thing is coming into 1. I would say the limit as x approaches 2 is 1. Let's just confirm it by looking at that graph. Notice as we come in from the left, as we come in from the right, we got this height value of 1. So, limits that fail to exist. There are 3 different types of limits that fail to exist. Behaviors that differ from the left side versus the right side. When they don't agree, the limit does not exist. Another type of behavior that fails, or where limits fail to exist, are unbounded functions. Things that go to infinity or to negative infinity. And the third one is oscillating. An oscillating function where it's traveling back and forth so quickly that it's not settling into any particular y value. So the common types of behaviors associated with non-existence of a limit are written there more formally. We just kind of summarized it. Absolute value of x over x. And then we want to know what's happening as x approaches 0. Well, let's just kind of put this in. So if I go -3 absolute valued over -3, this appears to be 3 over -3. This has a limit or a value of -1. Do the same thing here. Absolute value of -2 divided by -2. Well, that would be like 2 divided by -2. It's -1. Same would be true there. 0, it is undefined at 0. I cannot use x equals 0 in my function because of the denominator. Put in 1, I'd have absolute value of 1 divided by 1. Well, that is 1. Put in 2, I'd have absolute value of 2 divided by 2. And that is 1. 3 over 3 is 1. So this function, it's undefined at 0, and then it's 1 everywhere else. So undefined at 0, but it is 1 when it's on the right side of 0. Over here, we always got -1. So when it's at 0, it's undefined, open circle. Otherwise, the function's value is -1. You tell me, what is the function, the limit as x approaches 0 of this function? Well, from the left side and the right side, they are not at the same height. This does not have a limit. It does not exist. And this would be an example where the left side does not agree with the right side. And that is one way the limits fail to exist. I'm going to have to stop this video now because we're reaching about 16 minutes.